And thank you everybody for joining this presentation. In some previous presentations covering the DE-4000, we have talked somewhat about the scripting environment and the scripting capabilities that are built into the DE-4000. But today's session is going to be focused entirely on our advanced scripting capabilities and control strategies that are enabled through this scripting platform. So while we have covered some of these topics briefly before, today's going to allow us to take a deeper dive into the scripting capabilities, give you some information if you have an interest to start learning how to take advantage of this, the scripting functionality, give you the resources that you need to start learning or to learn more about the scripting platform and what it can do for you. And then also share with you some examples, real-world examples of where we've implemented this scripting platform and what it's enabled us to deliver to our distributors, our customers, and our end users. So it's certainly not a necessity that you be a script programmer to be able to use or configure the DE-4000. And as Dave mentioned, we have plenty of resources in-house that we can make available, either to assist you in using the scripting platform yourself, or for providing custom solutions that we are able to provide. And because of the power and flexibility of the scripting platform, it allows us to provide those advanced capabilities much more quickly than we would with other types of resources. So let me jump right into today's presentation. The first question, what is scripting, and how does it compare from traditional computer programming or computer code? So just my definition of scripting is it's code that's interpreted real time without the need to pre-compile. So in the past, when programmers wrote computer code, they would have to go through a compiling step to actually take that code and interpret it into something that the computer can use. But with scripting, it's actually interpreted real time as it's used, and because we were able to avoid that pre-compile step, it gives us a number of advantages, and one of those is being able to write script and run it immediately and see the results and not have to wait for compilation. Now, there are many scripting languages that are available and in use throughout the world on all kinds of different platforms and products, such as Python, Java, JavaScript, and Lua, and many other scripting languages. But we've chosen to use Lua in our scripting environment, and there's a number of reasons for that. The speed of Lua is pretty much unmatched compared to other scripting languages. The stability, Lua's been around since the 80s, so it's very stable and proven. The readability of the scripting language itself, it's probably one of the languages that's closest to just plain English in terms of its readability. It uses words and text quite often more than punctuation and symbols as is used in some other scripting languages. So it makes it easier for people to pick up and learn. And Lua has a broad user base, and it has great support for embedded systems. Lua is used in a lot of today's advanced video games. World of Warcraft and other video game platforms use Lua extensively because it allows people to customize their environment or create new extensions and add-ons and platforms very quickly. But it's also used in commercial industrial applications such as how we're using it. So If you want to learn more about Lua, the best resource is Lua.org, and on that website you'll find documentation for Lua. You'll find history and information about Lua, the language itself, and who developed it, and how it was developed. And you'll also find a web page that allows you to run a live demo of the Lua code. And so what I'm going to do right now is just jump to that Lua Live Demo, and here's the address for that. It's lua.org/demo.html. And so what this demo page allows us to do is just write brief chunks of Lua code and then execute them and see the output. Now, in every programming language, typically the first program that's written is what we call Hello World, and it's just, no matter the language, the goal is just to get some output that says Hello World. And so with Lua, it's just as simple as a print command, passing in a single parameter inside of the parentheses, and then the double quotation marks indicate that this Hello World is a literal text string. So basically we're just telling it to print this text, Hello World, and so when I click Run, you'll see an output box appear below with the text Hello World. Again, that's just a introductory program that you'll see oftentimes with any language. Let me just give you a little bit more advanced example. So in this case, I'm creating a couple of variables. The first variable is first name, and I'm using my name, Brian. The second variable is last name, and then I'm creating a third variable called full name, and I'm basically adding my first name together with my last name, or concatenating them. And so the addition symbol for strings in Lua, instead of the plus sign, it's actually 2 periods. So the variable full name will be Brian plus Worth, and then it will print that. So let me run that, and we see the output there is Brian Worth. So let me get into examples that are more real world for our industry and more practical for something that's actually usable. So in this case, I'm creating a variable called first stage suction, giving it a value of 93, a variable of final stage discharge with a value of 1232, and then a calculated variable called differential, which will be assigned the value of final stage discharge minus first stage suction. And then finally I'm going to print the statement total compression is, and then the double period, which adds to that the actual value of the variable differential. And when I run that, it says total compression is 1139. Now we have capabilities in Lua to add logic or decision making based on the value of variables and so on. So let me show you an example of what we call an if then else statement. So I've got suction pressure at 90 pounds, a target pressure at 85 pounds, and then a differential, which is the suction pressure minus the target pressure. So I'm wanting to maintain my suction pressure at 85. It's actually running at 90. And so this if statement says if the differential pressure is greater than 0, then print suction pressure is above target, and then it'll print that differential. Else it will print suction pressure is below target. So let me run that. Oops. Oh, there we go. So if you make a mistake, it'll correct you and tell you what line number. Let me run that again. So it's saying suction pressure is above target and the differential is 5. Let me change this to say 37. Run that again. Suction pressure is below target. So these are all just static examples of writing a bit of Lua code in this demo and executing it. But what's certainly more interesting is being able to run code like this on the DE-4000 and look at the similarities and some of the differences of running Lua code on the DE-4000 versus this platform we're looking at right now. So what I want to do is go on it. All right. So I'm going to open up our DE-4000 virtual environment at electronicvms.ddns.net. There we go. Okay, so this is our virtual DE-4000. Again, it's available at electronicvms.ddns.net. And what this allows us to do is run a virtualized DE-4000 and take advantage of all the scripting capabilities without having to have direct access to the hardware of a DE-4000 system. So we've covered in previous sessions how to configure the DE-4000 and set up channels, so I'm not going to really spend any time on that. So I'm going to go straight to the scripting. So if I go to the Global tab and go to Scripts, you can see that there are 4 script editors. One is the master script. There's a control script, a Modbus script, and a demo script. We're going to focus mainly today on the master script. So a big difference between the master script and the demo script, the Lua.org demo page that we were just looking at previously, is in the DE-4000, this master script is run continuously. So whatever code you write in this master script, about 4 times per second, the system just runs that script over and over again. And that allows us to have continual control over what's happening in the DE-4000, and it allows us to constantly update calculations and respond to changing conditions. So what I want to do here is set something up that's similar to what we had in the other environment, where we can essentially print or output a message. So I'm going to create a new function here called output, and I can pass any sort of text into this output function. And what this function is going to do is create a virtual channel using this command set svert. And the name of this virtual channel is going to be output. And then the value of this virtual channel is going to be the text that was passed into this function. So if I just say output hello world and then save that, now the system is running that script over and over again. So if I go back to my dashboard screen, I can edit the dashboard and add a new display element and filter down to my virtual channels. And here we have the virtual channel that I just created called output. And the content of that is hello world. And you can't really tell, but it's actually printing that over and over again 4 times per second. It's not just static. So if I go back into scripts, rather than just printing hello world, what I can do is create a loop counter. So I'm going to one thing that's really helpful is being able to sorry about that. One thing that's really helpful is being able to check if a variable exists or not. So I can say if not loop counter. In other words, if this variable does not exist, then I can assign it a value. So I can say loop counter equals 0, else loop counter equals loop counter plus 1, and then end. And the last thing I'm going to do is just say output loop counter. Now in this case I'm not using quotations because I don't want to output a static string. I want to output this variable called loop counter. So that's why it's different than the other examples where I put a string like hello world inside of double quotes. But in this case I'm just passing in the value of this loop counter variable. So let me save that. And when we go back to the dashboard, we can see that that counter is incrementing. Now it's incrementing at about 4 counts per second. If I want to do something that's actual time based, let's look at how we can access the system clock. So instead of using the loop counter, we have a function called getTime, and what getTime does is it gives us the system time represented as just a very large integer value. And in computer programming, we refer to this often as epoch time. So I'm going to just assign a variable called epoch and say that epoch equals getTime. And so all I'm doing is assigning that the output of that getTime function to a variable called epoch and then outputting that epoch variable. So if I save that and go back to the dashboard, there is the current time displayed as a epoch time, which is a large integer number. If I go back to my script, one thing that's very helpful using this getTime function is we can do things like keep track of how much time has elapsed. So what I can do is I can do a check for this variable that I'm going to create. So basically if this start time does not exist, then start time equals getTime. And then I'm going to create a variable called elapsed to calculate the elapsed time. And for the output, I'm going to just abbreviate the word elapsed, and then after that, print the actual elapsed time. Oops. There we go. So you can see now it's calculating how much time has elapsed since the script started running and displaying that. Now we can also do formatting of the numerical value, and we can round it off to remove the decimal point. So if I go back to my script, there's a function math.floor, which basically just chops off the non-integer part of the number. So now I have my elapsed time there. It's just a whole integer value. So again, let's do something that's a little bit more applicable to our industry. So I'm going to load a configuration that I've already created here. So one nice thing about the virtual DE-4000 is you can load an existing configuration file and make changes to it, and then export that back out. And then you can take that same configuration and load it into an actual DE-4000 system, and it'll work just the same way as it was working in the virtual environment. So what I've done here is I've created two channels, one for suction pressure and one for discharge pressure. Because this is in the virtual environment, those channels really don't have any value, but I'll show you in a minute how we can force those channels to a certain output value in order to test our calculations. So if we look at the script that I saved as part of this configuration, we're saying that the variable called suction pressure is going to be assigned the value of the input channel that's on terminal module number 1 and input channel number 1. So this is a new function that I'm introducing here called GetChannelVal, and whatever channel is configured on terminal module number 1, channel number 1, the current input value of that channel will be assigned to this variable suction pressure. Then I've done the same thing to get the value of channel 2, and I'm assigning that to discharge pressure. So if we go back to our dashboard, this suction pressure, if I click on the gauge, it takes me to the configuration page for that input channel, and you can see it's terminal 1, input number 1. It's got a label of suction pressure. So that's where the script is getting that value from, is from that channel number 1 and channel number 2. And then we're doing a differential calculation and saying that the differential equals the discharge pressure minus the suction pressure. And then we're using that output function from before to set that to a virtual channel, and we're showing some text to show that that's the differential between those two channels. So if I go to the dashboard, now this is a really nice feature of the virtual environment. We are able to use the test mode, which is typically used on a real DE-4000 to trigger channels while an engine's running and test the input without actually shutting down or faulting the engine. But in this case, in the virtual environment, when we turn the test mode on and we click on a channel such as this discharge pressure, it pops up an input box and allows us to type in a value. So I can type 1235 and hit enter, and it actually sets the value of the discharge pressure to that number that I just typed in. And then I can go to the suction pressure, and let's say assign it a value of 49. And so our script is doing that calculation and subtracting the suction pressure of 49 from the discharge pressure of 1235 and showing us that the differential pressure is 1186. And as soon as I update either of those channels, then the output changes to reflect that. So again, here's an example of doing calculations based on various input channels and then displaying that output on a virtual channel. Now we don't have to use this output function. Well, it's not the only way. We can create virtual channels just directly in our script. So what I want to do here is I want to set up a virtual channel to keep track of my maximum discharge pressure. So let me go back to the dashboard and set that discharge pressure back to 0. And then let me go to my script. So this function getSvert allows us to get the current value of a virtual channel. And if that virtual channel has not been assigned or created or assigned a value, there's also a second parameter here that allows us to assign a default value. So what I'm able to do is say that Discharge Max is the value of this virtual channel, and so what I'm really doing is getting any previous value that may have been assigned to that, and then I'm going to compare that to the current discharge pressure. So I'm going to say if discharge pressure is greater than discharge max, then discharge max equals discharge pressure. And then the last thing I'm going to do is write that discharge max back to the virtual channel. So I'll say set svert discharge max, and then the second parameter is the actual value to assign to that. So that's going to be our variable discharge max. So let me save that. So now that I've created a new virtual channel called Discharge Max, I want to add that onto the dashboard screen so that I can see the value. So I can filter down to my virtual channels, and here's my Discharge Max. And so it's currently at 0 because we haven't had any discharge pressure other than 0. If I make sure my test mode's on and set my discharge pressure to 800, you can see that the discharge max now has updated itself to 800. If I go to a lesser pressure, it's still showing that my max was 800. So now if I go to 1200, it's updated the max, but if I go back to a lesser value, it's maintaining that max. So that's something handy where maybe you want to be able to leave the unit and come back and know what was the maximum value that the discharge pressure reached while you were away, and you can assign that to that virtual channel and view it that way. When we looked at the scripts page, everything we've been doing so far is in the master script tab, but we also have the control script, the Modbus script, and the demo script. I won't go into the control script a whole lot other than just explain what it is. So we have under global control, we have a control page that allows us to set up a dual input split range control strategy that allows us to, for example, control speed if we want to based on suction pressure or discharge pressure, or we can do both simultaneously. We can also add a second output channel, so if we want to control speed and also a recycle valve, for example, we can do all of that on this page, and we do that by enabling a channel and assigning that, for example, to our suction pressure, and choosing the choosing which analog output we want to assign for our speed output, and so on. So I'm not going to go into this control strategy anymore at this point in time, but what I do want to explain is that if we go to the global scripts page, under control script, it's empty by default, but we can provide the script that we use internally to drive this entire global control strategy that's on this page here, and allow you to modify that all of that scripting that we've developed internally and create your own custom control strategy, but still take advantage of all the user interface elements that are on this page to define your inputs and your outputs. And we were able to use that recently with a customer that wanted a third output. So instead of only controlling speed and the recycle valve, they also wanted to do some additional control of their field suction controller. And so we were able to expose that scripting and basically just copy and paste the script that we use internally into this editor page, and then go in and make changes to that and give that customer a new version of that control strategy that added that third output channel. So it's very very useful for doing that. The Modbus script is also empty by default, but that's where we can create a custom Modbus mapping or add new Modbus registers, or maybe you've created a virtual channel that you want to be able to access over Modbus. So maybe you've created a pressure differential or a temperature differential channel, and you want to be able to read that and assign that to a Modbus register. That can all be done in this Modbus script editor. The last editor page I want to talk about today and give you some examples is the demo script. And on a DE-4000, on actual DE-4000 hardware, anything that's in this demo script is just ignored. But when you're on the virtual platform, what this demo script allows you to do is automate the values. So instead of having to go into test mode and type in values for certain channels, you can automate that. And what that allows you to do is test your startup sequences, for example, or control strategies, or any number of things without having to be on the actual hardware. So if we have in our startup sequence, if we have permissives that are set, it may be difficult to get past those permissives if we're trying to run in the virtual environment. But when we use the demo script, we can force values into those channels that meet those permissives and allow us to continue on through the startup process. So I'm going to load another configuration file that I created previously. And this will allow me to demonstrate how we use this demo script. So what I have currently is a pretty standard startup sequence. So I have I shorten the times just so we're not sitting here waiting, but we have a 3-second warning state at state 1. We have a 3-second prelude at state 2. We start our starter motor in the crank state number 3. State 4, we activate the ignition. State 5, we activate the fuel valve. And then in state 6, we're going to just wait until the engine RPM reaches 400 RPM. And so what you'll see is, if I try to go through the start sequence, it'll go through the warning state, it'll go through the prelude, through to the crank start, the ignition, the fuel. Oops. It actually went beyond the, I forgot this example already has that script in place, so let me. I'm going to remove this script temporarily. So without anything in that demo script, when I go through the startup procedure, it's just going to stay at that crank weight until it sees engine RPM that's greater than 400. Okay, so now we're in this crank weight state, and to get beyond that, I can make sure I've got test mode enabled, and I can actually type in an RPM that meets that permissive, and then it will move on. But if I want to automate it so I don't have to just constantly be changing all of these values, I can do that with the scripting. So let me stop. And you'll notice also when I stop, the engine RPM doesn't actually stop because it's just set at whatever value I set with the test mode. So if we go back to the global scripts and go to the demo script, so I'm introducing a new function. This one's called GetState, and what GetState does is it just returns which of those startup sequence states that we're currently in. So if we're in prelude and I say GetState, it's going to give me back a value of 2. If we're in this ignition state and I say GetState, it'll say 4. So if I go back to my script, so I'm creating a variable called engine state and assigning it the current state, and then I have 2 if statements, and the one says If engine state equals 0, then set speed value to 1. I'm sorry, speed channel 1 to a value of 0. And if engine state equals 5, then set speed value of speed channel 1 to a value of 500. And then I can even go on and say that maybe when I'm in my warm-up state, I want to have, which is 7, I want to have the speed be 750 RPM. And then when I'm running, maybe I want my RPM to be 1200. So I'm going to save that. And I want to point out one other thing in my startup sequence. In the warm-up, I have a permissive for my engine oil temperature at 900 or 90 degrees, and I also have a permissive for my compressor oil temperature at 90 degrees. So you'll also see that we'll get stuck in our startup sequence at state 7, but I'm going to go ahead and start up and let it run to that point. So again, when we reach the crank weight state, then we should see our engine RPM jump up to 500, which it just did. And that allowed us to get beyond that state and into the warm-up. And now the engine RPM is running at 750. But now it's stuck on the engine oil temperature permissive and the compressor oil temperature permissive. So again, I could set each of those to some value greater than 90, and so as soon as I've set both of those, then it will continue on into the running state, and as soon as it went to running, you saw the speed jump up to 1200. And again, when I stop, the speed goes back down to 0. So what I want to do now is actually set the engine oil temperature and the compressor oil temperature in my demo script so that I don't have to set any of these values manually. So again, in state 7, I'll do set channel value, and it's terminal board number 1 and channel 3. I'll set that to 90, and I'll do the same for channel 4. And I'm going to set everything back to 0 so that we can make sure we don't have to. I'm going to turn off test mode. So this time it should go through the entire startup sequence. Actually, I should set those values so they're above 90. So let's set one to 95. We'll set the other to 120. Okay. So now it should go through the entire startup sequence and get us all the way up to running without me having to manually override any of the values. So this is a pretty simple example. We're only modifying the engine RPM and a couple of temperatures, but we use this extensively in-house for our own development, and we have very complicated control strategies where we have blowdown sequences and pocket loading sequences and different things that we're testing. So we may have 20 or 30 or 50 or more values that we have to constantly change in the scripting and through that demo script that allow us to step through and test these very complicated control strategies, valve control, again, pocket loading, and so it's the same tools that are available to you to use on this virtual environment. We use extensively for our own testing and development. So that's pretty much what I'd like to share at this point. I may step in at the end of the session and share a few more things. But what I'd like to do for now is turn the time over to John Nance, who's going to talk a little bit more about some of the ways that we've used and leveraged the capabilities that come with this scripting environment. And John Nance and Tim Webster are going to share with you some more real-world examples of what we've done and what some of our customers have done, and some of the advanced control strategies that we've been able to develop with this scripting environment. So at this point, I'll turn the time over to John.
Well, thanks, Brian. I'm going to kind of defer. Tim and I kind of had a brief meeting right before this class started today, and Tim's going to show some insight to some of the script first, and then at some point he's going to cue me to start sharing my screen, and I've got an actual running demo where we've taken the script that he's used to develop some very, very detailed algorithms. And actually we have all of these running out in the field in one way or the other right now, actually in real live working conditions. So with that, Tim, if you want to start sharing your screen and show what you want to, just whenever you're ready, cue me and I'll flip over and we can actually show a running unit with some of your algorithms that you've been working on via script.
Yeah, thank you, John. We've done 3 primary functions so far. I'm going to start with the simplest one. The simplest one is our what we're kind of calling a dynamic lube. Essentially, it's similar to what Brian had mentioned earlier, where you could take the control functionality from the existing DE-4000, pull that script into the control section, and make custom changes. We're doing something similar with the lube. There are default lube settings in the global setup, and we can take all that script out, put it into the script editor, and make adjustments. And what the dynamic lube is doing is essentially it's like a floating lube set point based on RPMs, and then we've also added the floating alarms and shutdown set points above and below that. So as the machine comes up to speed, it can shift these set points up and down, so it's a little more dynamic instead of just having a hard limit. It doesn't override the hard limit. The hard limit is still there as a maximum, but this gives you more flexibility in the lube control circuit. I did want to just show a quick snippet. We're not going to go through the entire script here, but some of the key things that we've done. We have a create parameter function, which you may use quite often in any scripting that you create. And we'll show you what that does when John starts sharing his screen, because he's got all that running and active on a test set there. But we're able to basically create a whole sequence of parameters that the operator can use on the machine to set certain set points, like the maximum, frame RPM rate, the shutdown set points, alarm set points, stuff like that. So, and this has got a lube 1 and a lube 2, which pulls over from the default generic lube setup. So, John, do you want to share your screen now? I think that'd be easier. And then it'll become a little more clear. All right, so John's got the lube setup. We have an under lube and over lube. We've got our alarm set points, and we've got the flow cycle time, and then we have a calculated lube rate, which is the dynamic lube rate. We also have some delay timers that you can go in there and say, okay, during startup, we want to ignore any alarm or shutdown condition during a predetermined amount of time during startup, just until everything settles down and gets you into a steady value. We don't want it to trip while it's in the process of starting up. If the calculated lube rate shifts off a little bit, that's like a pause. It says, hey, we're going to run this once we get past the timer, but until that timer's done, it's going to ignore any alarm condition or shutdown condition. So all of these values on the dashboard, these are values that we've created in the parameter section, or like Brian's earlier examples, we've created a virtual variable, an svert, for the values that we put in, and then we can display them on the screen. So now eventually this all will get rolled in. We want to roll this into the low level, and then this stuff will just be there all the time. But until then, we'll have to actually run drop the script in and run these functions, and they'll all be available to build custom dashboards. You want to pop over to the parameters screen real quick, and we'll show them that, and then we'll come back to the dashboard.
Sure, yeah, I want to kind of point out a couple of things before we leave the lube, but let me get into the parameters for the lube. See that?
Yep. Yeah, so all those...
sorry, let me...
There we go. So all those parameters that we created in the script, those all cycle into this params page that's under the global. It makes it a kind of a one-stop shop for all your parameters, makes it convenient to go down through and set any of these set points right off the bat. And we built in the functionality to be able to disable this temporarily, so that's why we have the dynamic flow enable. Real simple, you put a number 1 or a number 0. You put the 0 in, it's going to disable it. It won't run any of that functionality. It's still there, built in, it's just turned off. Once we put the 1 on, it's going to enable all that and do your alarms and shutdowns based on your set points. All right, John. What do you want to show them on the main dashboard there?
Sure. So I have the overlube shutdown set at 50%, and the underlube shutdown at 50%, and the alarm values underlube and overlube set at 10%. These obviously aren't real-world parameters, but I'm trying to keep this unit running here in the lab and not accidentally knock it down as I start changing some values. And we go back to the main dashboard. What was really funny, the very first time, day one, Tim and I worked this out and we were ready to take it to the field, the very first unit we put it on, they went from using just a simple proximity switch to where they had a high kill set on their time at about 160 seconds, which is obviously better than a traditional old DNFT that might have been defaulted at 3 minutes. But no one was ever worried about overlubing. And the very first unit we installed it on in the field, not only while we were installing the necessary hardware or software on the unit, they were the mechanics were working on cylinders, the third stage cylinder, because they had discharge valves out. Well, every one of the valves that was damaged that they pulled out of it had fractured valve springs, and or some had a slightly cracked plates. It was really funny when we fired it back up. We found that they were grossly overlubing by using this algorithm. And so Tim was kind enough to set some debounce timers in here, but I cannot, it's not really easy for me in the simulation to change my actual cycle time because I'm just using a timer relay. But I'm going to drop the RPM down. If you caught it when we first switched over to this screen, you'll have seen that we were overlubing. So my cycle time is going to stay the same, but as I slow the RPM down, the calculated lube rate is going to change immensely, and we'll see everything refresh in a moment. And so will our overlube alarm. So now it's set at, it's shifted to 27 seconds. Now in a real working unit, as the speed changed, so would the cycle time, because the speed in which the lube pump is being forced. But Tim has some really nice debounce features in there, because we know that units are going to be sped up and slowed down, so we don't want to trigger an alarm or a shutdown event too suddenly. So what we'll see here is about 60 seconds when it times out, we should see this channel go into an overlube alarm. And so my point in bringing this up and telling you the story about the damaged valves that we found with the overlube, okay, so there's our alarm, is overlubing can be just as critical and detrimental to the health of a compressor package out there running in the field as underlubing. So now that we've gotten that alarm, I'll speed it back up, and within about 60 seconds, once everything returns to normal within parameters, we should see that alarm clear out. But Tim, that's all I had. I don't think we need to see the alarm clear out if we want to move up to the next feature.
Yeah, the next function that we created was rod load. Now this one here, this is the tandem one, right? Tandem cylinder?
Yes.
Okay.
How'd you guess?
Yeah, because you're missing a few things.
Yeah.
So we're working on this right now. It is a little cumbersome. We have to do some customizing per application. But down the road, we are working with Brian and some of the other people on the team to add some features to the user interface that will make it easier for you to set up your geometry, which then, as you know, anyone that's done rod load calculations, it's all, customized to the geometry of that unit. So we need to make sure we have, cylinder diameters, rod diameters, and then the configuration matters too, whether it's a single acting, double acting, or tandem configuration. So essentially with the rod load, it's real simple. In the parameters, we don't have to go back and look on that, but essentially we have a maximum compression and maximum tension rod loads that you'd enter in based on the specs of your unit, and then it takes that into account. You enter in all your geometry and the parameters as of right now. Again, we're going to try to make it a little easier for you guys moving forward, but we want to prove out the functionality of it. And then what it does is it does calculate the current rod load. We can, and we'll touch base on this when we get into the temperature stuff that we've done, but essentially we can do the rod load based on actual pressures, and then to get true rod load, we want to actually do the offset pressures to compensate for the loss internally. So, and you can see John's pointing to them there. We have offset pressure values in there, which we'll cover in the dynamic temperature. But essentially, we can have the rod load look at either pressures, whether it's the actual pressures from the transducers or the offsets that take into account the loss. And then all of that's displayed here as a percentage of maximum. You've got, in this example, cylinder 1's a double acting, so it has both compression and tension percentages. And then cylinders 2 and 3 are tandems. So you got your compression on cylinder 2 and your tension on cylinder 3 that work in tandem. We have alarm set points for those percentages. And then we can do shutdowns as well. So
you want me to show those alarm points, Tim?
Yeah, go ahead, jump in there. All right, so
yeah, go ahead, Tim.
Yeah, so here under the rod load safety, again, we can enable or disable the rod load just like any of the other functions we've done. But then we have our alarm for compression, alarm for tension, shutdown as well for compression and tension. We have some buffers in there, debounce basically to protect from any spurious values as things shift. And then we also have a start delay that we can put in there as well to give you a buffer during the initial startup. Below that, we have the geometry. Again, it's a little cumbersome in this setup, but as we make improvements, we'll make it easier for you to put your geometry in there, and we can use that geometry across several different algorithms and control strategies moving forward. So we'll have a centralized place for that. So there's your maximum rod load compression and tension values. And yeah, I mean, there's not much to that. Anyone that's manually done, like John has, the rod load calculations know that it's a relatively simple calculation, but we want to make it as user-friendly as possible and set it up for that specific unit.
One thing that I'd like to point out before we leave this and move to the temperatures is Tim did touch base, and he's going to key in more on these offsets. But if anybody's ever seen some other products out in the past that are running the rod load calculations, a lot of times they're not accurate. They're off when it comes to simply measuring suction pressure and discharge pressure on a cylinder, because those are external pressures. And the calculations that they were using also has to do more with the older slow-speed machinery. In the high-speed world, that doesn't work too good. And so these offset pressures are designed to not only compensate for the valve losses across the valves, but they're also designed to compensate across the machine. So we can use discharge pressure for the first stage to calculate what's going across the first stage cylinder, but we can also use discharge pressure for the first stage to become suction pressure for the second stage. So we can do two completely different offsets, because we know that there's going to be a huge pressure drop as we go through the cooler and the process piping, and then across the valve, ultimately into the second stage. So these are very, very key in this rod load algorithm, as well as the temperature that I believe Tim's going to show next.
Yeah, so the last thing is the temperature offsets. Essentially, just like our other two functions, we have alarm and safety shutdown set points that we can put in, but there's a lot more going on in the background. There's a whole series of calculations that it has to do to offset, like John said, to compensate for the losses and shift those pressures. There is a lot more information that you have to enter in the parameters. Now John's created this screen here to allow him to calibrate a unit. And I don't know, John, if you want to explain that briefly, and then we can pop over to the parameters and show them all the specifics as you're going through how you would calibrate a unit using this setup.
Sure. So let me just kind of explain this machine. When we have, or this page, we have to understand, first off, in gas compression, what affects temperature, what affects the discharge temperature. Now, once we know that, this becomes pretty easy, a pretty simple, easy layout. So again, this is a two-throw, three-stage tandem arrangement. So RPM is very instrumental in temperatures. You know, the higher the piston speed, the higher we can see temperatures, as well as inlet temperatures. So these are just two examples real quick of parameters that we're actually monitoring. We're actually monitoring the driver speed. We're actually monitoring the inlet temperatures. Now, or say a base level package that's out in the field, which this is really modeled around one, the only additional sensors that we've added are the 3 inlet temperatures. Now, because I'm in a lab, I don't too much care what my actual temperatures are, but here are my actual temperatures that we're monitoring. I don't have anything hooked up to them right now, and I ran out of lab simulators, so that's why they're showing negative 475. Now, how we calibrate this in lab situations, getting prepared to go out in the field, is we actually are doing compressor performance runs with the software, and it's more important for us to make sure that these numbers across the bottom match. But let me pause on this for just a second and explain why this is so important. People for years, if we go back, say, 20, 30 years, the rule of thumb was people would set the discharge temperature kills at 10% or 25 degrees above normal operating parameters. As control systems have become more an integral part of how we control a compressor, though, 30 years later, we have a lot of different things that are constantly changing and driving. And we've gone from a dominant market out in the field of slow-speed machinery to high-speed machinery. And so what we see happen out in the field a lot of times is people will set discharge temperature kills at too high of a level. So we still have that function with our discharge temperature channels. We still have a hard kill set. In this case, it's set at 310 degrees Fahrenheit. But if we have applications out in the field where the cylinder is actually only discharging around 180 degrees, if the operator or the mechanics that take care of this unit have that temperature set at 310, chances are they could lose compressor valves or even rings in a cylinder. Yes, they'll heat up, but they may not reach that critical temperature that's hard set at 310 degrees. So the whole concept of this is we calculate what the actual temperature is across the bottom. Then we can then turn around and create floating alarm set points and floating safety shutdown set points. So we can set those then at a tighter tolerance because they're always moving based on pressures and the dynamics of what's going on with the compressor on the location. We can now set tighter windows of tolerance, but yet still allow the compressor package to have a wider ratio span and or a wider RPM span. And the mechanic now is not forced to rely on this one fixed kill that he or she set way up high above 300 degrees Fahrenheit. Tim, I'll hand the floor back to you and let you kind of drive this as we demonstrate this, and I'll just kind of show what you talk about.
All right. Well, first, let's jump over to the parameters and show them some of the values that they're going to have to enter to get this to work for them. Again, we have the enable that lets us turn this on or off, and that enable actually also is used in the rod load to tell the rod load whether or not to use the offset pressures versus the straight pressures. So if you've turned on the temperature, dynamic temperatures calculations, then rod load's going to use those as well. So you don't have to do anything else there. If this is on, rod load's going to use it. You have a start delay on these and the alarm and shutdown debounces as well that are all customizable for your application. Each individual cylinder has a discharge and suction offset percentage, and then the alarm and safety shutdown percentages. And we have those for each individual cylinder. We have, go ahead, Joe.
Yeah, sorry, Tim. I wanted to point out something. For this demonstration today, I just used an erroneous value of 10% offset. And so what that does is that takes the external measured suction pressure or discharge pressure and offsets it 10%. But a keynote there is, rather than having the field tech guess, Tim was genius enough to put in a thing to where if we offset the discharge pressure 10%, it's a higher value than what we're measuring, because we know that the internal pressure of that cylinder is going to be greater than the external pressure. If we offset the suction 10%, then it's a lower number inside the cylinder. If that makes any sense to anybody that really understands the mechanics of gas compression. So that was one little feature that's just really easy. Now, about these percent offsets, how do we actually calculate what they should be? To date, what we've been doing, if I go back years ago, an analyzer was how we used to match these numbers, a real-world mechanical analyzer, to where we can get the pressure volume and the pressure time cards off a cylinder because we want to know what's really going on in the cylinder. What we found for our testing to date is that most performance run softwares these days will actually, once you do the performance run based on a set of real-world conditions, it'll actually give you a theoretical pressure volume card. Now, I'm not going to sit here and say that all performance runs are equal, but the ones that I've been using have been getting us real close. So these numbers in real world, when we're tuning a system, will actually be they're generally usually somewhere in the neighborhood of 0 to 10%, but 7.5%, 9%. So this is where it really takes a person to set one of these up and tune it out in the field. It takes a person more than the lowest mechanic. It takes a guy that knows the mechanics, it takes a guy that knows the performance, and has the ability to run the compressor performance software and understand it, or an analyzer. Of course, back to you, Tim.
Yeah, so the next section, you enter the RPM values. You'll enter the maximum RPM for the unit, and then you'll also enter the percent offsets for your stages, and that calculates into those offset calculations, taking into account the adjustment for the RPM. And then you have your ratio of specific heat, obviously your ambient pressure. We can hard enter a number here, but that also could potentially be a sensor on the unit if you had that available. And then your K values for your individual stages. And that should be everything you need. Now we're down in the lube. So those are all the values that you got to put in to get this to actually do the offsets.
Yeah, I think if we change the RPM, if you focus bottom left on just the number one cylinder theoretical discharge temperature at 260, you won't see much of a change with RPM with a value entered in at 1, but you will see it'll drop down as we slow it down a little bit. And at the same time, the actual calculated temperatures reducing so are our alarm limits and our safety limits. Let's speed it back up. And just as easy, lower our suction pressure a little bit. I can't see it on the screen, but we will see our theoretical temperatures, because we've lowered the suction pressure, increase. And exponentially, as the theoretical temperature increases, so do our alarm limits and our safety limits. And Tim was kind enough to also put a debounce on that, because again, if you're going the opposite way and you're still running a little hot, sometimes, you know, even though the calculation may be calling for cooler temperatures, it might take a minute for your actual thermal well in your sensor to cool down a little bit. So Tim was kind enough to put a debounce in.
And obviously we made that adjustable because, you know, some units are a little faster to adjust than others. So we wanted to make it as flexible as possible for the application.
And you'll even see a change if I change the temperatures. If I can figure out which knob to turn.
And while he's doing that, all these values that we've created and been able to put on the dashboard here, like Brian had mentioned earlier in the Modbus scripting, we can take any of these values and output it through the Modbus so that you can gather that data in a SCADA system of some kind, or you know, have it trigger an external device. So we have that capability to take any of these values and pump it out through Modbus. And John, unless you have something else you want to go through with this, I think we've covered the basics for all three of those algorithms.
Yeah, I'm pretty satisfied that we've shown them everything. I'm having a little trouble with getting suction temperatures to increase or decrease, so we'll just kind of skip over that. But I think everybody gets the point on that. I'm fine with opening up the floor for questions and answers. Or Tim, before we do that, do we want to talk about some of the other algorithms that we're working on, like the channel grouping for temperature, vibration, et cetera, et cetera?
Yeah, I mean, most of these are that were in the works, and we have nothing to show right now for them, but we're working on some grouping and averaging where you can create different groups and then put specific channels into those groups and take averages across those, and this will allow you to see what the overall average for a set of temperatures or vibration or any group. And then also when you have an outlier that's failing, we can see that we could do a comparison and see how far off from the average a particular channel is. So you can point to that and say, okay, something is going to fail, and try to catch failures before they actually cause any damage.
And one of the critical factors of there is if you're monitoring, let's say, engine main bearing temperatures, and you have the kill set at 210 degrees, 220 degrees, but yet you're starting a cold unit up and everything's starting out around 30 degrees, during the warm-up process, if you have one main bearing that drifts X percentage away from the others, even though it has not reached 210 degrees where your shutdown set at, it can alert you to where you have both an alarm, a deviation alarm, a high deviation alarm, or even a high deviation shutdown. For anybody listening in that has ever smoked a center main bearing on a Waukesha or an old Climax engine, you might appreciate that. So, Tim, I'm ready to open the floor to for questions and answers if you are.
Well, Brian, you mentioned you might come back here at the end. Is there anything else that you wanted to add?
Yeah, thank you, John and Tim. I really appreciate your overview of some of the more advanced control strategies and algorithms that we've been able to implement with the scripting. I did want to cover one more thing before we do open up for questions.
Do you need the screen, Brian?
Yeah, please, and I'll share my screen. Okay, hopefully you can all see my screen there. I wanted to talk a little bit about the parameters because the examples that John and Tim shared had quite a number of parameters, but I wanted to just stress the point that those parameters are things that you can create in your script. They are not pages that we have to develop internally in our, through our user interface development team. They're created directly in your script and instantly available for you in your development or for your users once you deploy your application. So I wanted to just give a quick example. I've got a differential pressure working again as I had showed before. So if I change my discharge pressure, say to 500, and my suction pressure to 32, I've got a differential of 468. But let's say we wanted to set a alarm limit based on that differential pressure, and if it exceeds some limit, then it would indicate an alarm status. We can do that with the parameters. So if I go to global and go to params, you see it's just an empty page, but as soon as you create a parameter in your script, it will show up on that global parameters page. So if I go back to scripts, here's the script where I'm calculating the differential. I'm just reading the suction pressure, the discharge pressure, and taking the difference and setting that to a virtual channel called differential. But I want to show you how easy it is to create a parameter and start using it. So all I do is at the top of my script is I call this function that Tim had pointed out earlier. The function is called createParam, and the first argument is the name of the parameter variable, if you'd call it that. And you can name your parameters whatever you want to, and then you'll use those later on in your script. The second item, or second argument, is a default value. So when the parameters first created and displayed on the parameters page, it will come up with this default value, but then the user can change the parameter to whatever they want it to be. The third argument is a category or a grouping, and what this does is allows you to create multiple parameters that will be grouped together on the parameter page with a header. So if you've got, as Tim and John were showing in their examples, if you've got 40 or 50 or 100 parameters, they're certainly a lot easier to use when you can scroll down and find a given group, and then maybe there's only 5 or 10 parameters in that group, and they're kept together. And then the last argument is basically usage text or help text that's displayed to the user. So here I just have help text of enter differential alarm limit, category of differential pressure. And so once I actually create the parameter, then in my script, I can use code that references that parameter. So what I want to do here then is add an if statement, and it's going to look at the differential, which was just the discharge pressure minus the suction pressure, but it's going to compare that to the value that the user has set in the parameters page. So we use getParam, and then we use the same parameter name here that we defined when we created the parameter. And we can also use a default value here. So if the parameter hasn't been created, instead of getting an error, it will just use this this default value. So basically, I'm saying if the differential pressure is greater than this parameter, then we want to create some output text that says differential alarm. Otherwise, we want our output text to say differential normal, and then we will display that output text in a new virtual channel. So we'll call it a set svert. And we'll just call this differential alarm. So as soon as I save that and go to the parameters page, now you see the parameter differential alarm with the default value and the help text and the category differential pressure. So I can assign whatever value I want that to be. So I can set that to 200 and save that parameter. So now if I go to my dashboard screen and go to test mode, set my suction pressure at 80, set my discharge pressure to 180, then my differential is 100. Now if I add the new virtual channel that I just created, which was differential alarm, so again, I'll set this to 80 and 180. It's showing me that my differential pressure is within the normal range. So if I exceed my set point of 200, so let's say I go to 500, and now my differential pressure is 420, then it shows I'm alarmed. But if I go to back to the parameters and change this to be 1000, now when I go back to the dashboard and set this at say 50 and this at 800, my differential is 750, which is now still within my my alarm condition. But if I set this to 1575 and now my differential is 1525, it's exceeded my new set point, and now it's alarming again. So anyway, the global parameters allow you to create interface for the scripting that you create, so that you don't have to go into your script and actually edit your script to change limits and set points or values that you want to use in your calculations. You can expose them on the parameters page and start using them and testing them and make them available to the actual end user of the scripting that you're creating. So that's really all that I wanted to share, in addition to what John and Tim had shared earlier. And again, we appreciate everybody for sticking through this this session, and we'll open it up now if anybody has any questions.
Brian, John, Tim, thank you very much for last hour and a half, hour and 40 minutes. As usual, session was excellent and well presented. Good material. Folks, any questions for these gentlemen on this topic?
Hey, Brian, this is Mike Porter. In one of our last, a few weeks back, one of our meetings, Paul McHenry mentioned something about pocket loading. And of course, I'm the old slow speed guy, so and that got my attention. And I don't expect you to go into detail on it, but can you give me an overview of how we're doing that?
Sure. I believe it was Andrew and Tim as well in our panel shop that helped create the actual pocket loading application that we created for a customer.
And I'm guessing what I'm curious is, Brian, is what are we looking at when we load pockets? Are we actually calculating horsepower or throughput, or I mean, how do we know how much to load the pockets?
Yeah, I don't know the specifics of I believe it was a Waukesha engine. I don't know the specifics of what the compressor was. I know it had 4 pockets that we could load, and in that instance, we were loading the pockets trying to achieve a target discharge pressure. So as long as our discharge pressure was below the set point, and we were also monitoring, I believe we had rod load calculations on that configuration as well. So as long as we were within an acceptable rod load limit and below the discharge pressure set point, we would load the first pocket, and then we had a delay that was configurable. And after that delay time, if we were still below the target set point, then we would load the next pocket, and that would continue on as long as we stayed below the target set point and within the acceptable rod load limit.
What about overloading the engine itself?
What's that?
What about overloading the engine itself?
I believe we had I believe we were able to read horsepower or some parameters that were coming from the engine. I don't.
Okay, that's good. I don't
know the specifics, but yeah. Anyway,
the stuff that you do is absolutely amazing to me, as you can imagine. And there's applications out there that we've always had to go to Allen Bradley on, and I feel that we're getting really close. If we're not there, that maybe we can go after some of this other stuff that we would normally have gave up to the PLC people. So anyways, after the first of the year, I'll get with you guys and tell you what my thought process is, and get John Nance and everybody on the same call. And again, John, you probably know what I'm talking about. It's a 3600. So anyways, that's all I had. So I was just curious where we're at. So
sounds good. Thank you for the question.
Okay, thanks, Brian.
Thank you, Mr. Porter. Anybody else for Brian or for John or Mr. Webster? Going once, going twice. All right, folks. Brian, Tim, John, any last comments before we let these folks go?
Okay. Sorry, Dave. I was trying to unmute my microphone. Yeah, I mean, if anybody has any questions and ideas about applications, just feel free to contact any one of us. But again, these algorithms that Tim and I have been working on and installing out in the field on test in test beds. We have a grand plan of embedding them in the system. I think Tim mentioned that, and having them available with geometry sections. But I just wanted to be clear. I mean, if somebody has ideas about applications today where they're needing this, and these are, like I said, going out to the field, we can make that happen. But again, the concept of adding these calculations that constantly float by the real world measurements that we're constantly getting. So it's a live calculation that's always happening and drifting, but that allows us to set these floating shutdown points up, is just to tighten the window and try to prevent such things as rod non-reversal failures, crankshaft, which leads to crankshaft failures and even compressor frame failures, et cetera, et cetera. So it's all intended to add enhanced levels of protection that weren't formerly, there in any systems.